audible? Okay. So thank you very much for the very kind introduction, and it's my great pleasure to be here. So before I begin, I would like to thank the department, especially Professor Tarun Kumar Das and Dr. Ranveer Singh for the kind invitation, and of course several other people. But these are the people that I have been talking with. There are going to be two lectures, so one in the morning and one in the afternoon, but not on the same topic. But the morning is more for master's level students, as I understand. And so what I'm going to talk on is the Egorychev method for computation of combinatorial sums. And summing up combinatorial sums is a very age-old topic, right? And the idea is that whether one can actually formalize and systematize analyzing such combinatorial sums. Right? So you have a very complicated sum, but it just turns out to be something really simple. Right? So for instance, if you take so in my so while I'm lecturing, I'll also write on this. Right? So for instance, if you start with something like MC0, right? So this sum, this is the same as what? What is the sum? 2 power n. Right? But you see that on the left hand side it's a bunch of combinatorial terms, and on the right hand side, so this is actually equal to 2 power n. And by the same token, if you just put alternating signs, MC0 minus MC1, that turns out to be equal to 0. And it's quite remarkable if you actually think about it, that you actually have something which is on the left it looks complicated, but on the right it becomes really simple. So what we want to do is we want to see if there is a way to formalize analysis of simplification of combinatorial sums. So that's going to be the main topic. Okay, and so what we are actually going to do is use complex analysis. Sorry? Okay, and by the way, please feel free to ask any questions. I have 23 slides, but I will do a lot of calculations. It's not like I have to go through all the slides. So if you have any questions, please feel free to ask. Okay, so what we actually want to do is we want to use complex analysis. And the way we are going to do complex analysis is the following. So mainly what I'm going to use is the residue here. Okay, and but let me just quickly recap. This is something that's already familiar to you. So suppose you have a function, but this is not holomorphic, but holomorphic. Okay, so if you have a function which is holomorphic, but holomorphic in a deleted neighborhood, that is, it is holomorphic in like a neighborhood, but minus a point, right? So if it is holomorphic in the entire disk, then what you have is that you have a convergent power series expansion, but you will not have any of the negative terms, right? But suppose you have a function which is holomorphic in a deleted neighborhood, something like this, then if you use Cauchy's theorem and then go through these steps, then what you will have is the Laurent series expansion, right? So the Laurent series expansion will have both positive as well as negative terms. Right? So that's what it is. And we say that the residue, this is the definition. So the residue of f at, let's say, the center point z0, where the function is not holomorphic, is defined to be the coefficient a minus 1 in this expansion, that I have. But you see that this residue is intimately connected to an integral, right? So this residue is actually intimately connected to an integral, because suppose I were to integrate this particular function, but for mod z minus z0 is equal to epsilon, where epsilon is some positive number. Actually does not really matter as long as epsilon stays in a small neighborhood. It does not really matter. But let's take epsilon to be a small number, and suppose I'm going to integrate both sides. Now, because of uniform convergence, you can interchange the sum and the integral, right? So now the integral goes into the sum, but now the claim is that because this is a disk centered at z0, right? Many of these terms are going to vanish, right? What are all the terms that are going to vanish? Actually, everything except one term. Why? Because if you have something which is holomorphic, right? So the Cauchy's theorem tells you that integral along a closed this one is going to be equal to 0. But it is also true for something which is not holomorphic, provided it has an antiderivative, right? So everything except 1 over z minus z0 term is going to disappear, because anything other than 1 over z minus z0 will have an antiderivative if it is negative, or okay, even if it is positive. But on the other side, that is, if it's a positive term, it's going to be 0, but just from your knowledge of Cauchy's theorem. So my point is, if you have a Laurent series expansion, then from the Laurent series expansion, you can relate that to an integral, and the integral is simply the coefficient a minus 1 that comes up in the expansion, right? So now this is the idea. So the idea, and this is the basis of contour integration, right? Sometimes real integration is simpler when you take it to the complex scheme, right? But this is the basic idea behind contour integration, that you want to integrate something, but that integration you can relate it to the coefficient of the Laurent series expansion, specifically the coefficient a minus 1 in the Laurent series expansion, right? So this residue is a minus 1, right? So this is what I'm going to exploit. Okay. Okay. Now, how do you calculate residues in certain simple instances? So remember, the residue is if you have an expansion an z minus z0 raised to n, but this can go from minus infinity to infinity. You need to isolate the coefficient a minus 1, right? But suppose you already knew that the thing is, if you have negative terms, then this is what you say. If the negative terms ends at a finite stage, right? Then we say it's a pole, and it's a pole specific to the number of negative terms the highest negative term that appears in the Laurent series expansion. But suppose you already knew that it's a simple pole. That is, it's a pole of order 1. That is, in the Laurent series expansion, this starts from not from minus infinity, but from minus 1. Right? So then all I need to do is just find I need to find a minus 1. But a minus 1, you can find it simply, right? Why? Because you just multiply by z minus z0, and then you let limit as z goes to z0. Every term will disappear, because for a minus 1, you had something like this. You had a minus 1 by z minus z0 plus a0 plus a1 z minus z0, etc. Now you are multiplying this with z minus z0, and then as z goes to z0, all these terms will disappear. This goes, only this terms are left. Right? But this is for the case in which it's a pole of order 1. But suppose it's a pole of order 2. That is, now what you have is, you have, let's say, a minus 2 by z minus z0 square plus a minus 1 by z minus z0, etc. But now what you need to do is you need to isolate this term. So if you just let if you just multiply by z minus z0 square, and then you let z go to z0, then you will not isolate this term. You will isolate this term, but that's not what you want. What you want is this term. But in order to do that, you just differentiate, and then you let z go to 0. Then this is just application of Leibniz rule, right? Because what you will have is, you will have something of this form: a minus 1 times z minus z0 plus some holomorphic part, right? Now when you differentiate, you are going to get a minus 1, right? A minus 1 plus other terms, but that all those terms are going to disappear because you have multiplied with z minus z0 square. So when you take one derivative, there are still going to be one z minus z naught in each term, at least one z minus z naught in each term to play with, therefore it's still going to go this way. So in general, you can actually do this for if you knew that it's a pole of order k. That is, if it ends at k, in the negative terms ends at k, then you can use this formula to calculate the residue. Okay, so I wrote a lot of things, so let me just erase this over here so that this is visible. So the residue of f of z at z naught is this. This is a simple formula that you can actually check if you know that it's a pole of order, finite order. Okay, alright. Now there is one more thing that I want to do, which is the following, that this is typically not, people don't typically talk about it in the first course in complex analysis, but once you also consider the residue at infinity, then the residue theorem has a very, very nice meaning. The Cauchy's residue theorem has a very, very nice meaning, and that's what I want to emphasize. So, suppose you have a function which is holomorphic, but now outside a large radius r, right? So then what you can do is you can still consider a Laurent series expansion, right? That's the Laurent series expansion, right? Now what I want to do is I want to consider the residue of f at infinity. But residue of f at infinity is that now you can make infinity to 0 by taking this z going to 1 by z. But that's not how residue at infinity is defined. The residue at infinity is defined by this 1 by z square, f at 1 by z, and with a negative sign. So there are three players over here. F at 1 by z. So that brings r z bigger than r into a smaller into a neighborhood, deleted neighborhood of 0, right? But there is also this 1 by z square, and there is also a negative term. Okay, let me explain why this is the motivation for the residue at infinity. Right now, this 1 by z square term comes up because if you consider this 1 by z, and then you differentiate, it's a change of variable formula for the integral, right? So if you consider that, then that becomes minus 1 by z. That also explains why this negative sign. So let me explain why this is the residue at infinity, or this is the correct definition for residue at infinity, right? So what we are going to do is, because it is holomorphic outside a ball, outside a disk, so this is R. So your function is holomorphic here. So now you take any R1 bigger than R. So that is something like this. Now you consider the integral. Mod W is equal to R1 f of W dw. But now, one thing for you to notice is the following, that the orientation that you need to give, so the positive orientation, if you were to consider the integral, is the anti-clockwise orientation. But now your function is not holomorphic in a deleted neighborhood inside. The function is holomorphic outside. So therefore the orientation, the positive orientation that we need to give is a clockwise orientation, because so what we think of as a positive orientation is that as you go along the curve, your domain should always be to your left, right? So now, because your function is holomorphic in this region, right? So what you need to do is you need to go clockwise, so that because as I go clockwise, my domain is on the left. So that's the positive orientation. So therefore, remember that this mod W is equal to R1 is given a clockwise orientation. Okay. So now let's do a change of variable. W is equal to 1 by z. So if you do W is equal to 1 by z in that integral, then this is what you get. You get f of 1 by z. You get a minus 1 by z squared dz. But now what happens to the orientation? So the orientation, when you consider W is equal to 1 by z, your clockwise. So when you do this variable, this change of variable, W is equal to 1 by z, what happens is that whatever was on mod W is equal to R1 now became 1 by R1. Correct? But not only that, the orientation was clockwise there. But now when you do this 1 by R1, 1 by z, it becomes an anti-clockwise orientation. So now you have by this process you see that mod z is equal to 1 by r1 is something in a smaller neighborhood of 0. But this mod z is equal to 1 by r1 has a positive orientation, in the sense that it has an anti-clockwise orientation. So this is a correct orientation. So now you see that, now you consider this integral. So now everything makes sense, right? Because this is how I define the residue. And that's the motivation, right? So this is what I have written here, so that mod w, the w is equal to 1 by z makes the orientation positive. Okay? So now let's go back. Now if I consider the Lorentz series expansion a and z to the n for the original function, right? So now what we need to do is we need to consider 1 by z square summation a n 1 by z to the n, right? So that's exactly what we have over here, right? That's exactly what we have over here. But now you see that if I integrate this, only one term is going to survive, right? Only one term is going to survive, because now I have to integrate this particular function in a small neighborhood of, in a disk centered near 0. But when I integrate, every term except one term is going to be 0. What is that term? The term corresponding to n is equal to minus 1. Because when n is equal to minus 1, then this becomes z minus of minus 1, which becomes plus 1 minus 2, which is minus 1. 1 by z dz, that integral is 2 pi I. Everything else is going to be equal to 0. So therefore, from here you extract only a minus 1. But that's not the residue, right? Why? Because if you see here, there is also a minus sign. So therefore, the residue is minus a minus 1. So therefore, my point is this, right? That this is the motivation for why we define this to be the residue. But if I consider the Lorentz series expansion, so this is for mod z at least r and less than infinity, which is over here. I just start with that. And then all I need to do is just look at the coefficient a minus 1 in that expansion. And then put a minus 1. That's it. That's going to be the residue at infinity. Okay. So now that I have all the things in place, right? So the Cauchy's the residue theorem is typically not stated this way, but this is the most natural way to consider, which is the following. So let's say we have f be holomorphic in C, the complex plane, except possibly finite number of isolated singularities, right? So there are finite isolated singularities, but you also consider infinity as a potential isolated singularity. Then what Cauchy's theorem tells you is that the sum of residues of f at these points, including z1, z2 up to zn and infinity, the sum of the residues is always 0. Right? So if you also take the residue at infinity, then the sum of the residues is going to be equal to 0. Now why is this useful? Right? So the reason why this is useful is the following. Because the sum of the residues is equal to 0, right? I have given the proof over here, but the proof is literally the same that you typically see in a complex analysis course, except that you also have to take the residue at infinity. And the residue at infinity, the fact that it is minus a minus 1 is what sets the stage. But why is this useful? The reason why this is useful is the following. Let's say you have to compute a contour integration, but the contour integration has 10 poles inside, right? But now what I can do is, because I know that the sum of the residues, including the finite poles and the infinity, is equal to 0, instead of computing the poles at these 10, instead of computing the residues at these 10 points, all I can do is compute the residue at infinity and then use this residue theorem in this generation. Right? So instead of doing 10 calculations, I am only going to do one calculation, which is the residue at infinity. That's the advantage. Okay? So what is the proof over here? So the proof over here is the following, right? So let's say there are these finite singularities, right? Z1, Z2 up to Zn. Now you consider a circle, right? A circle that encompasses these finite poles. So let's say you have somewhere over here, but you take this circle to be large enough so that it encompasses all these things. But now you give this circle the clockwise orientation, the anti-clockwise orientation. This is a positive orientation. That's a positive orientation. Okay? So then what you have is, so then we have the following, that 1 over 2 pi I integral mod z is equal to r f of z dz is equal to the sum. These are all finite. This is z1, z2 up to zn. This is just Cauchy's theorem. This is just Cauchy's theorem. Right? And this integral is equal to the sum of the residues at each of these finite poles. Right? Each of these finite poles. Okay? Now, what I need to do is I just need to compute this integral over here. This integral. But remember what we did in the previous stage. In the previous stage, I took this mod z is equal to r, but I gave this the clockwise orientation. Right? So when I did the clockwise orientation, the answer turned out to be equal to minus a minus 1. That is negative of a minus 1. But now I have given here the positive orientation. In the sense that this is a positive orientation for the region inside. So therefore this integral is now going to be not equal to minus a minus 1. This integral is going to be equal to a minus 1. So therefore what do I have? I have this. A minus 1, which was the Laurent series, the coefficient a minus 1 corresponding to the Laurent series expansions in the region between mod z, between r and infinity. So that's a minus 1 plus is equal to this quantity over here. But now you just take this to the other side, so you get minus a minus 1 plus these residues is equal to 0. But we have shown that this is actually the residue of f at infinity. So the residue of f at infinity plus the residue at the finite singularities is equal to 0. That's Cauchy's residue theorem, including the residue of infinity. So the sum of the residues is equal to 0. But if you are only going to consider the finite poles, that's not true. You also have to consider the pole at the singularity at infinity. So if you also take the singularity at infinity, this is going to be the. So this is the Cauchy's theorem. The sum of the residues actually vanish. That's clear. Okay. Now why am I saying all these things and then combinatorics? So here is where we are going to see where combinatorics comes into action. Okay. So let's look at this. N choose k. Right? Now n choose k, I can actually write this in the following integral. 1 plus z to the n by z to the k plus 1 dz. Why is this true? Because let's just expand this 1 plus z to the n by binomial theorem. So 1 plus z to the n is summation n choose k z to the k. Now you divide, or maybe I should not use k. I choose r, z to the r. R is equal to 0. So now you divide by z to the k plus 1. Which term is going to survive? When you integrate over this closed contour. Everything except r is equal to k is going to disappear. Right? So if r is not equal to k in this whatever I have written over here, if r is not equal to k, then the function is either holomorphic or it has a antiderivative. So antiderivative over a closed contour is going to be equal to 0. Right? So therefore the only term that's going to survive is the one corresponding to r is equal to k. That's exactly what it is. So now you see that I can use complex analysis to treat combinatorial. This is the basic idea behind Egorychev. Okay. Now in some instances the following is going to be useful. So instead of looking at that representation, I can look at this representation. N choose k is equal to 1 over 2 pi I 1 over 1 minus z to the k plus 1, z to the n minus k plus 1 dz. I will come to this in just a second. Actually, I will tell you why this is. Now, let's say you want to find a function. So this is a characteristic function on between 0 and n. That is, it is 1 from 0 all the way up to n, and then 0 outside. Right? So let's say you choose n. So 0, 1, all the way up to n. At exactly these points, you want the function to be 1, and everywhere else they will be considering positive. So everywhere else it has to be 0. Right? So this is what is called the indicator function or the characteristic function. So this characteristic function, you can actually write it in the following, in this fashion. Why is this true? This is quite easy to see, because mod z is equal to epsilon. Right? So therefore, and if I choose epsilon to be small enough, 1 over 1 minus z as a convergent power series expansion. And what is the expansion for 1 over 1 minus z? Tell me, Shai. Zero to infinity. Let power up. This is the geometric series, right? So now let's consider. So what we have k plus r by z to the n plus 1. Right? Or in other words, this is going to be integral z to the k plus r minus n minus 1 dz. Mod z is equal to epsilon. Right? Now, if you consider over here, so this is r over here. So if r gets beyond, let's say n, right? R gets beyond n. That is, r is at least n plus 1. Right? If r is at least n plus 1, what happens? Here. If r is at least n plus 1, this is going to be holomorphic. Therefore, it could be equal. And if r lies between 0 and n plus 1, then you're going to have one term, exactly one term, which is going to give the integral. And that integral is going to be equal to 1, because we have also divided by 1 over 2. So if you want to have, so why is this useful? Because you see that in some instances, you want to focus your sum to be between 0 to n, but it's better to treat the integral, it's better to treat the sum as from 0 to infinity. Why? Because suppose I were to consider this, right? Suppose I were to consider this from r is equal to 0 to, let's say, n only, right? Then this is not equal to this, right? This will have 1 minus z to the n plus 1 over here, right? But what I can do is I can put an indicator function, this indicator function, and then treat the sum as from 0 to infinity. I have an example. If I have time, I'll show you. But anyway, so this is the basic idea. So I want to use combinatorics using complex numbers. Now we still haven't proved this particular formula. N choose k is equal to 1 over 1 minus z to the k plus 1, z to the n minus k. So why is that true? Well, let's see. So let's start with the geometric series. 1 over 1 minus z is equal to summation m is equal to 0 to infinity z to the n. Now, I differentiate both sides. So if you differentiate k times, this is exactly what you do. I have run through the steps. You can check that if I differentiate once, then you get m z to the n minus 1. But you might as well run m from 1 to infinity, because m is equal to 0 is 0 anyway. So that's what we have over here. Then you just re-index it, and this is exactly what it is. So this 1 over 1 minus z to the k plus 1, you can write it in the following fashion. N is equal to 0 to infinity, n plus choose k, n plus k choose k z to the. So now let's go back. Right? So what we have is, in the previous formula, we had 1 over 1 minus z to the k plus 1, 1 over z to the n minus k plus 1. So we have n plus k choose k, z to the n by z to the n minus k plus 1. Right? Z to the n minus k plus 1. Oh, maybe I should use R. Sorry. Yeah, in this equal to 0 to infinity. Maybe I use R. Because n is already a variable. So if I use n as a variable, then it's not difficult. So I have r plus k choose k. Right? 1 over 1 minus z to the k plus 1 is r plus k choose k z to the r dz by z to the n minus k plus 1. Now I want to integrate this. Right? If I integrate this, so all I need to do is r minus n plus k plus minus 1 should be equal to minus 1. Because everything other than that, the integral is going to be equal to 0. Right? So what is the value of r? So minus 1 goes. R is equal to n minus k. So substitute. R is equal to n minus k plus k. So I have isolated n choose k by considering this contour integral. That contour. Okay, so 1 over 1 minus z. So in some instances, this particular representation is useful. In some instances, that representation is useful. Now it depends. It comes from a little bit of experience as to which one is going to work in which scenario. Okay. Okay. So now that we have given the basic tools for us to play with, let us see some examples. This I'll come back to it later. Okay. So I want to explain the basic idea of Egorychev method. Okay. And so let us consider the following example. I want to show that this sum, right? This summation s is equal to 0 to L minus 1 to the s, 2L minus s, choose L choose s, that's equal to this. Okay. Let us see. So what I'm going to do is I'm going to write this 2L minus s choose L as a contour integral, and this epsilon is some positive number but small. Okay, so I have 2L minus s choose L. This is equal to 1 over 2 pi I. Now whatever this power, right, I'm going to use the first representation. So if I use the first representation, that's going to be 1 plus z to the 2L minus s, and for the bottom I have z to the L plus 1 dz. Okay. Now this 1 plus z to the 2L minus s, let me expand in a binomial series, binomial sum. Right? If you expand this 1 plus z to the 2L minus s as a binomial sum, you get r is equal to 0 to 2L minus s, 2L minus s choose r, z to the L. Okay? So then what I do is I also need to divide by z to the L plus 1. But once I do that, this is what I do. So look at this. Right? So we have 2L minus s. 2L minus s. This is 1 plus z to the. Sorry. Here I wanted to explain why this is true, but I have already explained that. But now let's come back. Let's not expand. So let's come back. So I have 1 plus z to the 2L minus s. And then you see that I have this L choose s over here and also this minus 1 to the s. Both are there. Right? So let me just put this back over here. Now there is a summation in s that I have to perform. Right? So if I perform the summation over s, I just isolate all those terms which are independent of s and the one that depends on s. So for instance, from here, 1 plus z to the 2L, that comes outside. Z to the L plus 1, that also comes outside. What are the remaining terms? We have minus 1 to the s, L choose s, and then from here I have 1 over 1 plus z raised to s. That's exactly what I have. Now this is independent of s. This only depends, these are the only players that depend on s. But this is a very familiar binomial sum. Right? It's minus 1 to the s, L choose s, a to the s, which I know is 1 minus a raised to s. That's exactly what I have. 1 minus 1 over 1 plus z raised to, in this case, L, which is z by 1 plus z raised to L. Okay, but now once you substitute this, magic happens. So I have z over 1 plus z raised to n. That's exactly what I have. Right? This is what we found out here. Now, the terms outside were 1 plus z raised to 2l and z to the l plus 1. But now I just do some manipulation. I have z to the l, that goes away. 1 plus z to the l, that also goes away. So I have 1 plus z to the l by z dz. Now you expand this. If you expand this by binomial, I have L choose R, Z to the R, but every term except the first term is going to disappear. Then you will go to contour integration. And the first term is going to give you an integral 2 pi I, integral to be 2 pi I, but I have also divided by 2. That's what I did. This is the basic idea of Egorychev. Right? Now, of course, the thing is, this is a very bare bones version of the basic idea. But the thing is, if you have a combinatorial terms involving 4, 5, product of 4, 5, 6, and then sum of those terms, and then you want to show that this actually simplifies to something else, something really simple. Of course, then you need to be very careful about the choice of contours and everything. Right? So. Okay, so that's exactly equal to 1. Now let's see over here. So this will actually work it out. Summation n choose r, n choose k minus r, that's equal to n plus m choose k. So this is actually a very familiar identity. Right? Do you know? Okay, actually I have written over here. This is Vandermonde identity. Right? But there is a combinatorial proof of this. What it's saying is the following. Let's say I want to choose from n plus m objects, I want to choose k. Right? Now, what this is saying is split this n plus m as n object and m objects. Now you have a choice, right? So now what you can do is if you want to choose r objects, you can pick one from here and k minus 1 from here. Right? Or you choose none from here, all k from here, or you choose 1 from here, k minus 1 from here, or you choose 2 from here, k minus 2 from here, all those combinations. This should be exactly equal to picking out k terms from n plus m objects. So you see that the right hand side is n plus m choose k, the left hand side is precisely this kind of making a division and then doing this alternating. Both are the same. So we know that. So we already have a proof based on counting that these two are the same. Actually, this is not that. This is actually. So, yeah, this is right. Yes. So we already have a proof using counting that this is actually equal. But now let's actually give a proof using Egorychev. Now one thing that I have not emphasized here is the following. Right? I have specified that R, but I have not told you what is going to be the upper and the lower limit. Right? Okay, the lower limit is equal to 0, but what about the upper limit? So the upper limit is actually going to be dictated by what this value of k is. Right? But what I can also do is I can actually make this upper limit to be equal to n. Nothing changes. So let's see how this proof works first of all. So what you have is so let's consider n choose k minus r. So n choose k minus r. I'm going to use it as a contour integral. So I'm going to write 1 over 2 pi I integral mod z is equal to epsilon 1 plus z to the n by z to the k minus r plus 1 dz. Okay, and then what I have is, I have this n choose r over here, so let me just put it back over there. So now what we get? So now what we get is, so we get n choose r, and then you have z to the r, and then you have 1 plus z to the m by z to the k plus 1 dz, and then integrate. And this summation is over r, but now what I am going to do is, I am going to consider r is equal to 0 up to n. And the reason why I can actually go all the way up to n is the following, is that if this k, so the combinatorial terms will adjust itself. If this r gets beyond k, right? If this r gets beyond k, this combinatorial term is going to be actually equal to 0. So what you can do is, you can actually, without loss of generality, take the sum, so that, see, technically the sum is from r is equal to 0 all the way up to k. But I can without loss of generality make it go all the way up to n. So that makes life simpler, right? So now what is this you have? Summation r is equal to 0 to n choose r, z to the r. This is equal to 1 plus z to the n. And then you have 1 plus z to the m by z to the k plus 1 dz. But this is 1 plus z to the n plus n by z to the k plus 1 dz integral, but that is n plus m choose. I have it covered. Random order. This summation, oh yeah, sorry, yes, thank you, yes, you're right, this is a typo, yes, thank you, there is no, it's just n plus n choose k, yeah, there is no summation here. Now you can also use, I'm not going to do this because I want to go into some more exciting stuff, so you can actually try this, that this sum, this combinatorial sum is actually can be simplified into this combinatorial sum, again using Egorychev. Okay, this method. So let me not do this, but let me go into other interesting problems. And I'll come back to this if I have time. Let me not do this right now. I also want to give you, so there are several other, by the way, how much time do I have? 10 to 15. Okay. So I want to give you one more approach, right? And this is a method of generating functions. And so the theory is the following: is that and this is something that happens frequently in mathematics. And if you observe, right, you may not realize this, but you look at many of the proofs in mathematics. Right? Many of the proofs in mathematics. So, for instance, let's look at Pythagorean theorem. Right? All the known proofs that, at least to my knowledge, there are several. I think it's now close to 125 or something like that. But all the known proofs involve counting in two different ways, computing the area in two different ways. Right? So when I was a student, my teacher told me this, that magic happens when you add and subtract a suitable quantity. Right? So for instance, the fact that you have that the derivative, the Leibniz rule, comes from adding a suitable quantity. Right? Adding and subtracting a suitable quantity. Or for instance, if you want to do like if you want to do computing areas, but now a 2D integral, right? An integral in 2 dimensions. So what you have is that you do Fubini theorem, right? You interchange the order of integration. When you interchange the order of integration, miracles happen, right? So um, many different things come from changing the order of integration. Changing the order of integration is the same as changing the order of summation with a combination. Right? Looking at the same object in two different ways gives you a lot of insight into the problem. That's basically what I'm trying to say. Okay? Alright. So now let's come back to this. So now what I'm going to do is the following. So I have the summation k is equal to 0 to n, this quantity, but I want to show that that quantity is equal to 2 to the 2n plus 1 plus 1 by 3. Right? 2 to the 2n plus 1, 2 to the 2n plus 1 by 3. You see that the left hand side is a complicated combinatorial sum, but the right hand side is very simple. I want to give you two proofs and then stop over here. Okay? So the proof is the following. So let us set this f of n is equal to this. But now what I'm going to do is I'm going to consider a more complicated sum. Right? What is that more complicated sum? What I'm going to do is I'm going to multiply this with z to the n, and then I'm going to consider the summation in n. Okay, and then my whole point is, then after I have done a bunch of stuff, then I'm going to just isolate this f of n. In other words, what is the theory is that if you're just going to find this combinatorial term, that's going to be harder compared to finding the generating function associated with it. So what is the associated generating function? So let's consider f of n multiplied with z to the n, summation n is equal to 0 to infinity. I have summation n is equal to 0 to infinity. This sum f of n already came with a k is equal to 0 to infinity of this one. But now you see that this is one of the points that I wanted to emphasize. You're going to interchange the order of summation. Right? So if you interchange the order of summation, so I have k is equal to 0 to infinity, n is equal to 0 to infinity. Now I have this whole quantity over here. This whole quantity. Okay? So I have this n plus k choose 2k. Now I have set it up in such a fashion that that's the same as this n plus k. So I have 2z raised to n plus k, whatever this power is. Remember, k is fixed. In this summation, k is fixed. N is the variable. Right? So this n plus k over here runs from k to infinity. K to infinity. So I have this 2z raised to n plus k, and then I just have adjusted so that I get the same term as this one. Okay? But for this I just need to use this particular formula. This was the derivative formula that I gave on the here, this one. So I'm just going to use this particular formula. You see that here m runs from 0 to infinity, choose k, that's the same as z to the k by 1 minus z raised to k plus. So if I use that, this is what I have. So k is fixed. Remember, k is fixed. This is fixed. So r choose 2k, 2z raised to r. And then I'm just going to use that particular formula. So if I use that particular formula, then I get 2z raised to 2k, whatever that power is. So whatever that number is, 1 minus 2z raised to 2k plus 1. Remember? This one. So if you have k, this is k plus 1. This just comes from the derivative. Okay. That's what we have over here. Okay. Now let us just simplify. I have summation k is equal to 0 to infinity. Z to the minus k, z to the 2k, that disappears, leaving you with z to the k. 2 to the minus 2k disappears. So what I am left with is z to the k by 1 minus 2z raised to 2k plus. Now what I am going to do is, I am just going to write this in the same fashion so that I have a geometric series over here. So I have 1 over 1 minus 2z, let me just isolate that. And then I have z to the k by 1 minus 2z raised to 2k. But that's the same, when you sum the summation, when you consider the summation from k is equal to 0 to infinity, this is a geometric series, which is 1 over 1 minus z by 1 minus 2z square. I will just simplify. This is exactly what it is. 1 minus 2z by 1 minus 4z times 1 minus z. Now you can split this into partial fractions. I have 2 by 3 into 1 minus 4z plus 1 by 3 into 1 minus z. Now what I am interested in is in the nth coefficient. And remember my goal was to find the nth coefficient of this f of n. Right? So all that I need to do is just look at the nth coefficient of this and the nth coefficient of this and then consider the sum. What is going to be the nth coefficient over here? It's going to be 2 by 3. It's a geometric series, right? Summation 4 to the n, z to the n. Correct? From here. From there, it's going to be plus 1 by 3 summation z to the n. The coefficient is 1 by 3. This 4 to the n is 2 to the 2n, so it's going to be 2 to the 2n plus 1 the whole by 3, which is exactly what we want to do. Okay, so therefore what we have is, we find out the associated generating function. So in a way, the thing is this, right, is that you are making the problem more complicated. But what is lurking in the background is that you are also interchanging this order of summation. So you interchange the order of summation, the results can happen. Now let me show you the same thing with a contour integration. Okay, so this is what we wanted to prove, right? We wanted to prove that 2 to the n minus k, n plus k choose 2k is a right hand side summation. Right hand side term. Okay, so n plus k choose 2k, I am going to write it as, so this 2 to the 2n minus k, n plus k choose 2k. Now this is one of those instances where I am going to use, it's more convenient to use the second representation. The second representation was the following, that n choose k can be written as integral 1 over 2 pi I 1 over 1 minus z raised to k plus 1 1 over z raised to n minus k plus 1. So it's more convenient to use this particular representation, right? So k plus 1, so whatever this k, this was my k, that's going to be 2k plus 1 over there, 1 over 1 minus z raised to 2k plus 1, and then you have n plus k minus 2k, that is n minus k plus 1. I'm just using that particular formula. Okay, so then what we get 1 over 2 pi I, 2 to the n, 1 minus z, okay, and then you have z to the n, but now I just need to consider the summation in n, summation in k. This is summation in k. So the summation in k is going to be what? It's going to be there's a 2 to the k in the bottom, right? 2 to the k in the bottom. So it's going to be a geometric series. That's what I'm trying to say. So what we have is 1 over 2 to the k, 1 minus z raised to 2k, and then z to the k. So that's going to be the kth term in the geometric series. So I have 1 over 1 minus z by 2 into 1 minus z squared. We just simplify. I have all this down. We just simplify this. We are going to get 2 to the n plus 1, and then 3 to the z to the n plus 1. So this is just splitting into partial fractions, right? So I'm just going to split this into partial fractions. So this is what I have. And now we are back into the same story, right? Because you consider this geometric series expansion, and this geometric series expansion. The only thing is that you just need to take a 2 out, and then you have 1 minus z by 2. So because mod z is equal to epsilon, that's small. So z by 2 is still going to be small, therefore the geometric series converges. Okay. Now one thing that I have not mentioned, yeah. So one thing that I have not mentioned is that why I am allowed to take this k to go from. So ideally, you see that if this is n plus k choose 2k, right? Now remember that you have 2k in the bottom and n plus k in the top. So ideally, you would like to consider the summation from k is equal to 0 to n, right? K is equal to 0 to n. But I'm actually taking the summation from k is equal to 0 to infinity. Why? Because you see, let's say it gets beyond n. K gets beyond n. So then the top becomes, let's say, 2n plus 1. but the bottom becomes 2n plus 2. That combinatorial term is going to be equal to 0. You can actually see this from looking at the combinatorial representation using Egorychev method. Therefore, without loss of generality, you can actually take the summation to go from 0 to infinity, which makes life convenient. Okay, so this is like a short snippet of Egorychev method. Now, I have several other problems here as well. But now, if you want a real challenge, you can actually try this. K is equal to 0 to n, 2 to the minus k, n plus k chose k is equal to 2 to the n. Okay, and this is another challenge. Summation k is equal to 0 to n, k 2n plus k, that's 2n choose n plus k, this is equal to n by 2, 2n choose k. This also you can try, and I will stop here, but I just want to give some references for this. I actually mentioned this in the bottom. So this method was first conceived by Egorychev. So it's the integral representation in the computation of combinatorial sums. It's actually a very nice, there's a book, it's in the AMS book, wherein he has given, there's a lot of complex analysis involved in trying to understand combinatorial sums. And his motivation was to formalize the procedure of trying to understand combinatorial sums. Okay, and the generating function, so using the method of generating functions, this is there is actually an online book by Herbert Wilf, and there is also a very nice set of online notes by Marco Riedel. In fact, some of the examples here I have taken from there, which is actually the Egorychev method and the evaluation of combinatorial sums. So many of the examples here I've taken it from this particular online set of notes. It's a very fun topic in the sense that to me it's quite remarkable that you can have this very complicated combinatorial sum involving